Hello everyone, today we are going to be starting the electrochemistry unit with lesson 1, oxidation numbers. So this is a very important concept to grasp your head around. It is one of the concepts that I assumed that my students knew when they went to first year university. So when you go into first year, please come with the assumption that, with the knowledge that you can figure out oxidation numbers. They're very important in determining chemistry. So oxidation numbers, or electrochemistry, let's start with, is chemistry that involves this exchange of electrons. I've always said that chemistry is due to the movement of electrons, but a lot of the times if you're forming covalent bonds, for example, the movement is not such that the electrons actually change atoms. But in electrochemistry, we have chemicals that are interacting, and in that interaction, electrons actually shift from one atom to another. And this movement of electrons is something we call current, if you do it on a bulk scale. So all electrical energy that we use for the majority, other than sort of mechanical electrical sources, chemical electrical energy is performed by electrochemistry for the most part. So particularly oxidation reduction reactions fall into the electrochemistry section. This is where a chemical oxidation and a chemical reduction happen at the same time. This is usually by choosing two chemicals that are carefully matched to one another so that electrons will transfer from one chemical to the other. So let's look at an example right here. If you react metallic sodium with chlorine gas, then a chemical reaction will happen and you will form sodium chloride. But one of the things we know about sodium chloride is that this is an ionic compound. So this is ionic, and we discussed ionic compounds in great detail, but ionic compounds are not, we know that if we dissolve this in liquid, we would find that this compound is not sodium chloride as joined together, but it is in fact a sodium ion and a chlorine ion. Because of the difference in electronegativity, the electrons are effectively transferred from one element to the other. Now prior to this, the sodium did not have a charge and the chlorine did not have a charge. So in this case, the electrons, they had the correct number of electrons to match the number of protons on those atoms. Now that ratio is different. So each of the sodium atoms has transferred one electron to the chlorine pair, and by transferring two electrons to that pair of chlorines, they no longer need to form a chemical bond, and they separate and form chlorine ions. So when we complete this transfer, we are going to be left with a sodium with no electron, giving it a positive charge, and a chlorine with an extra electron, which means that the chlorine will have a negative charge because it has one more than the number of protons that it has. So we can define this process as one of two cases, either oxidation, where an atom loses one more electron. So in our case, oxidation was the sodium. So the sodium going to sodium plus, that's an oxidation. Let's draw that little Lewis dot electron. Or a reduction, which is the case where the chlorine happened, where the chlorine gained an electron. The chlorine went from having 7 valence electrons to having a full complement of 8 electrons. So if you have trouble remembering this, there's a mnemonic called Leo the lion says grr. Leo the lion is losing electrons is oxidation, and grr is gaining electrons is reduction. I've also heard oil rig, oxidation is loss, and reduction is gain. Whatever works for you. Try to make sure you can keep this in mind. I always think about oxidation is when the oxidation number goes up, and we'll talk about oxidation number in a second. Reduction is when the number goes down. So notice that the charge on sodium has gone to a plus state, so that's gone up. And the chlorine has gone to a minus state, so that is going down. So mathematically, reduction is that this charge, whatever it is, goes down. Now, sometimes we like to look at these things in a format known as a half reaction, which I kind of started to draw above. The half reaction is simply a reaction, a standardized reaction of a single atom and the number of electrons that's either gained or lost as a chemical reaction. So here, the sodium atom has lost 1 electron, so the product of the half reaction is the production of an electron and the production of that ion. On the chlorine side, the chlorine chemical has gained 2 electrons, creating a Cl-. And we'll see in a minute that we actually might use a different format a little bit. They might write out, you might find, especially on a half reduction table, you might find it written as this way: 1/2 of Cl2. And in this way, you can isolate for a single atom, as half reactions tend to look at single atoms at a time. And so in this case, we would get a single chlorine. I don't have to write a 1. A single chlorine minus, since we're talking about half. All right, let's look at another example. Here we have the magnesium metal reacting with oxygen to create magnesium oxide. In this reaction, the magnesium begins as a neutral atom, loses 2 electrons to become magnesium 2+, so it has lost 2 electrons, so that means that it has oxidized. Losing electrons, oxidation, Leo. So the magnesium is oxidized. The oxygen begins as a neutral atom and gains 2 electrons. So electrons, gaining electrons is reduction. So this is, the oxidation is reduction, or the reduction is the oxygen. The magnesium has been oxidized. And we can again see that the charge on the magnesium has gone up. It's gone from 0 up to +2, so that's oxidation. The oxygen has gone from 0 to -2, which is reduction. So there you go. And then we can see here is the half reaction expressed in terms of a single atom. Notice that in this case, the single atom actually absorbs 2 electrons. And so if you wanted to do this in a balanced way, we notice that we have 2 magnesiums and 1 oxygen. So actually there are 4 electrons being transferred in that chemical reaction, because each oxygen needs 2 electrons. And we can see them drawn out here as going into the 2 empty spots on that oxygen. If we think back to our chemical, or our first lesson, our first unit, we remember that oxygen has this p orbital where there are 2 open slots, and that magnesium is essentially going to fill in the open slots in that p orbital, and that would be the 2p on the oxygen. And so, there's a connection. This is why we usually do this lesson last, is it kind of brings us all the way back to the first unit. Okay, so oxidation numbers. Not all redox reactions are as simple as this. So chemists have designed a system to keep track of the electrons in a chemical reaction. They have assigned oxidation numbers to all atoms and ions. The oxidation number represents the charge the atom would have if every bond were ionic. This is important because this is only if every bond was ionic. Not every bond is ionic. That's true. And so we have to, but oxidation numbers work on the presumption that every bond is ionic to produce a sort of a helpful system for tracking electrons. It is, again, a model. This is going to be, the oxidation numbers fall into a model. They are good at predicting chemical reaction, but they are not truth. If you could actually, get a microscope out and zoom in on the atom and look at where the electrons are, it would probably be a lot more complicated than saying that the boron is missing 3 electrons and the oxygen has gained 2 electrons. It's not nearly as simple as that. Here we have on the periodic table, we'll find the common oxidation numbers. These common oxidation numbers are tightly related to the electron configuration that we learned in first unit. Especially the numbers, it's especially tightly related to valence electrons and the electrons in the highest energy orbitals. So for example, nearly every metal here has a +2 oxidation state, and that's because nearly every metal has an s orbital that is got 2 electrons in it. Some of the oxidation states, like scandium as a +3, is related to having a that s orbital and a single electron in its d orbital, and there's other things that we could connect back to our discussions in electrochem, and we actually in our atomic structure, and we did do a little bit of that as well back in the day. So we kind of covered a little bit of this before. So these are the most common states we'll find these atoms in, and this has influence on the way these atoms are found in chemicals and what kind of chemicals they can form and what kind of binding orders they have. So when you're assigning oxidation numbers, there are a set of rules you can use. We always go by atom, and the oxidation numbers of uncombined elements is always 0. So if it's a pure element, it's 0. So if it's magnesium, if it's oxygen, if it's hydrogen, if it's just a calcium atom sitting by itself, then those start out at 0. Once they become combined, then the entire chemical has to balance out to 0 as well, usually, if it's a balanced chemical. The oxidation number of monoatomic ions, so we're talking about ions here, is equal to that of the ion. So these are going to be ion charges. Those are true charges. Those are ones you can actually depend on. So for example, lithium, sodium, potassium, those always are +1 oxidation, +1 oxidation numbers, and they're also +1 charge. The compounds with oxidation numbers of the oxidation number for alkaline and alkali metals is always +1. Alkaline earth is always +2. The oxidation number of aluminum is always +3. And the oxidation number for fluorine is always -1. These are a couple of the standard ones that you kind of always have to assume. Now things start to get tricky as you move your way to the other elements. For example, hydrogen is assumed to be +1 unless it's a hydride, which we usually don't talk about much. But so they're very reactive chemicals where the hydrogen has a -1 charge. But don't worry about them. They're very, very rare. You can usually identify them by being the combination of a metal and a hydrogen, and that's it. There is no other compounds in there. The other example that's very rare, but is oxygen. Oxygen is very common, obviously, and in 99% of the time, even 99.99% of the time, you can assume that oxygen is a -2. Just as 99% of the time, you can assume that hydrogen is a +1. There are rare chemicals like peroxides and superoxides that are -1, even -1 even -0.5 and -1.5. There's some really strange compounds out there, but you don't have to worry about those. I'm going to avoid them as much as I can, but they are one of the reasons that peroxides are so reactive. For any neutral compound, the sum of the oxidation numbers must be 0, and for a polyatomic ion, the sum of the oxidation numbers for each atom must be the charge of that ion. So let's give a look at some examples of how to work this out. So for example, assigning the oxidation numbers for each atom in a sulfur dioxide. So here we have a sulfur and an oxygen. We do not know, we know that this is a chemical, right? So in total, the numbers that are up here have to equal 0 because there's no charge on that chemical. We know that oxygen is always a 2-, or a minus, is always going to be written out as a -2. Sorry, let's go. So notice that there is a difference between the ionic charge and the oxidation number. For example, the magnesium ion, Mg2+, has an ionic charge of 2+ and an oxidation number of +2. So we're going to make sure that we put our sign in front to show that we're talking about oxidation. -2 charge here in sulfur. So that means we have 2 -2s. And then what is the charge of the sulfur? That's the question we're trying to answer. So if the total is 0, then we know that that for each oxygen that is -2, we need to balance that out so that it all adds out to 0. So the only value that will be effective here is if we have a +4. So the sulfur is +4 because each of the oxygens is -2, and the total for the compound is 0. A chemical compound, a neutral compound, must sum to 0. Oxygen is always 2, -2. So if oxygen is always -2 and you have 2 oxygens, then you must have a +4 from the sulfur. Okay, let's try this potassium chromate. This should be very similar to when you were making ionic compounds, only now we might not be talking, we're going to be able to identify every chemical in there, not just the ionic ones. Okay, so here we have a case where we have quite a complicated system. We need to be able to add these up together. Oxygen is 7. There are 7 oxygens. Each oxygen is a -2. Each potassium is a +1. So, oh, you know what? I remember how I did this before. What I've done before, what I like to do is I like to keep track of those oxidation states on top because that's where we write them. And then what you can do is you can multiply through to create sort of a worksheet underneath. So -2 times 7 will give us a -14. +1 times 2, because there's 2 of them, will give us a +2. So that, and in total, this has to add up to 0. So what am I missing? Okay, we do a little bit of arithmetic here. We got a -14 plus a 2, that gives us -12. So that means that I need to be adding 12 here in order to get to 0. 2 plus 12 is 14, minus 14 is 0. Great, and now to find out the chromate, I need to go and do the reverse operation. I need to do a division here, which will give me a +6 per chromate. So each potassium is +1, each chromate is +6, each oxygen is -2. And you can do this in a variety of ways. I'm sure if you watch 5 videos, you'll get 5 different ways of calculating this out. All right, so here we have an iron nitrate. There's a couple of ways to go about this one. One is to identify the nitrate first and think about this as an ionic compound. So usually you'll have access to a polyatomic ion chart somewhere in your data sheets. And nitrate is a known polyatomic ion. It is a polyatomic ion with a -1 charge, and you have 3 of them. So you're doing them times 3. So that means that you have a -3 charge from those 3 nitrates. And so that means that the iron must be complementary to that. It must be a +3 iron. So that's one way to go about it. You can also play around with what we just did. So let's do that again, but let's do it with the method we just wrote out. So I'm going to write out my iron. I'm going to put a bracket, nitrogen, O, 3, 3. So now I just have to keep track of the bracket as I do things. So for starters, I have oxygen, and I have 3 of them. See, this is going to be tricky to do it this way. I think that we're going to have some troubles. I think our best option was before. Yeah, you know what? We're going to have to use that knowledge of the ion. That's the only way it's going to happen. Because if you don't know the ion, you won't know the nitrogen, you won't know the iron. Another option is to go back to your table, and you can use this table and use the common ions that you find there and play around. So for example, nitrogen has the most options, oxygen has the least options. So we could use some assumptions. We could say, okay, so if this is a -2 for oxygen, and we have 3 times 3 of those, so we have 9 times -2. That leaves us at a -18 in total. So what values should we put for the nitrogen? There are 3 of them. So whatever that is, we need 3 of them. It's probably a positive number. So let's go back to the nitrogen and see what kind of positive values it can have. It looks like it can have values from 1 to 5, whereas the iron has from 3 to 2. I still think you're going to need that ion knowledge, identifying that this 3 here is important, and so we're going to have to know that this iron is plus 3, and that's just going to have to come from the ionic compound aspect. And so if this is plus 3, then I'm short 15, right? I'm short plus 15. 15 divided by 3 is 5, so this is a plus 5. Plus 3, there's only one of them, plus 5. Okay, let's see if I can redeem myself with this next one here. I have an iron sulfate. Again, this is just going to be a lot easier if you can identify this as an ion. And you did do a bunch of work in KSP. Ionic salts, we should know how they break apart. This ionic salt is going to break apart into iron 2+ and SO4 2-. So now, starting from that knowledge, let's identify the oxidation states this way, separate this out as if it had just dissolved, and now work our way through. So this changes some of the rules for us. The iron is done. The iron is going to be equal to +2. There's nothing to talk about there. The oxidation state is equal to the monatomic ion charge. But for the sulfate, we have a total charge on the sulfate of -2. So that means our math is a little different. Instead of equaling 0 like we did when we did a whole compound, we're going to show it as equaling -2. We're going to still assume that oxygen is -2, so -2 times 4, that gives us -8. But now instead of saying that sulfur is a +8, we know that the answer is -2. So sulfur must be +6, because +6 minus 8 gives us -2. +6 times 1 sulfur gives us a +6 on top, or divided by, and there's our final answer. And we can also write it out now as the full compound if we like. We could go iron SO4, put a -2 up here, put a +6 here, and put a +3. And we should be able to find out that the math works out the same in either way. Okay, this looks like it's the same chemical compound, so let's keep moving along from that. Maybe we could switch this one out with something different later. Assign the oxidation numbers for each atom in copper sulfate. Okay, so what we can do is that we have the sulfate figured out. So now that we've done sulfate once, you don't need to do any more work. So SO4, we can just say this is -2 plus 6. That's fine. It's a sulfate. A sulfate is a sulfate is a sulfate. And it is normally, this whole compound is a 2-. So then what is this? What's the copper? If the chemical is 2-, or you know what, let's just leave it like this. We're going to do the whole thing. Okay, so now that you've figured out the sulfate, we can put our little worksheet down here. -2 times 4, -8, +6 times 1, +6, and then we have something divided by 2, something divided by times 2. So let's see what that would be. This compound adds up to 0, right, on top. So it's an uncharged. Once it's copper sulfate, it's not charged. So what charge does this oxidation state would we assign this copper? Well, it looks like I'm short by 2, and so 2 divided by 2 means that this copper is +1. All right, hopefully that helps you out. Have some fun with it, and good luck.